Hi everybody, welcome back. Our next installment in section 4.7 is going to be dealing with the inverse tangent and inverse cotangent. Think back. When we took a look at inverse sine and inverse cosine, we had to reduce the interval for where we allowed those two functions to exist for an inverse to exist. And again, we did that because we need to make sure that for a function to have an inverse, the function has to be 1 to 1. That is why we limited our inverse sine to be existing from negative pi over 2 to pi over 2. And we limited sine to become negative pi over 2 to pi over 2 for inverse sine to exist. Then we limited cosine to 0 to pi for inverse cosine to exist. Well, behind me, take a look. We've got tangent graphs. Now, the tangent graph kind of sets up a little bit nicer for this. It's nothing new that we have to remember, because when we take a look at the graph itself, you'll notice that the tangent function is broken up into chunks in between these vertical asymptotes. Well, you'll notice if we left our domain unlimited for tangent, we would still run into that issue where we are not considered a 1 to 1 function. So just like we did with sine and cosine, let's restrict that interval. Take a look. What could you restrict the interval of tangent to that still includes the origin and yet makes it 1 to 1? You'll notice the first thing you probably did is you looked right at the origin. And we have a tangent graph that is existing in between negative pi over 2 and pi over 2. So very similar to the inverse sine existence, the inverse tangent exists with one little change. So in other words, it's like I could eliminate everything that's to the right of pi over 2, okay, going further positive. I can eliminate all of that. I can eliminate anything that's happening to the left of negative pi over 2, and I essentially have my restricted domain for tangent to allow inverse tangent to exist. Now, the one thing we have to be careful of, though, is that when we think of the pi over 2 and the negative pi over 2 here, those are values that we cannot use in tangent. They're undefined. So when we look at the restricted domain here, so when we look at this restricted domain, if I write that in an interval here, is that this is an interval that is running from negative pi over 2 to pi over 2, except the difference is I cannot use those two boundary values. So instead of having brackets for the restricted domain like we do for sine, we have parentheses here. So inverse tangent will exist when we restrict our tangent graph to be in between negative pi over 2 and pi over 2, but not inclusive here. Okay, so that's the big difference. Inverse sine, it's negative pi over 2 to pi over 2 inclusive, brackets. Inverse tangent only exists when we allow tangent to fall between negative pi over 2 and pi over 2, but not inclusive, parentheses. Now, we're going to make the same argument here for cotangent. Okay, so as you look at the next slide, or if we, let's do some things with tangent real quick. Okay, since we've got tangent identified here, let's stick with that. So let's take a look at some examples. Now, the thing that we're going to find is that we're going to handle these problems exactly in the same way that we handled the problems for inverse sine and inverse cosine. For example, let's say that we're asked to evaluate. Okay, so I'm just going to take this out of here for just a minute. Take this out, move it out of the way. All right, so let's say we are asked to evaluate. okay? And they're going to give us inverse tangent values here. So let's say that they give us, and again, two different ways to write it. We can say arctangent, and in this case of 0. Now, just like we did inverse sine and inverse cosine, what we have to recognize is that when we take an inverse, what we are essentially looking for is an angle of some sort. So the goal is still the same. The goal is still to figure out an angle. But again, keep in mind, our angle we're looking for will be a radian angle or a radian value. Now, just like we did previous, we're going to rewrite this back into something more familiar. So we know we're looking for an angle, so we can think about this and say, okay, the tangent of the angle that I'm looking for has to be equal to 0. But again, think about what we did with that. We have to know that that angle is within a restricted domain. So this value, this angle, has to fall within the interval of negative pi over 2 to pi over 2. Okay? Now keep in mind where that's at on that unit circle. That's quadrant 4, but rotating in a negative direction, or in quadrant 1, rotating in a positive direction. So we need to make sure we can calculate our tangent values. Now, we don't need to make this hard either. This is probably where the bigger challenge is, because on the unit circle, we don't have tangent values that are calculated. It's not something you've been asked to memorize. So here's how we get to it. We know that we make the transition to tangent. Okay, so that hopefully makes sense, just like we made the transition to sine and cosine. But now, since the unit circle is dealing with sine and cosine, and we know the relationship of tangent is that the tangent of an angle is equal to the sine of the angle over the cosine of the angle, what we can actually do is change from tangent into that ratio of sine over cosine. Now, I know some of you are probably looking at that going, oh, wait a second, now that just makes more to look at. Well, yes and no. Stay with me for a second here. So I'm going to change this tangent of theta. I'm going to say it's sine of theta over cosine of theta. Now, we know the value is equal to 0. But here's the neat thing you can do. And this is literally what you're going to do with many of these problems, because they're still going to relate back to unit circle issues. Notice that I put a line under that 0. Notice I put the line under the 0. I spoke a little too soon. What number could we put on the bottom, or whenever we take an integer and we want to make it look like a fraction but without changing the value? You'd put a 1. Well, guess what? It doesn't have to be hard, because by making this a fraction over here, it is essentially leading us to positions on the unit circle. Now, because I started with a 0 here, this is what we get to look at. The sine value has to be 0. The cosine value has to be 1 on the interval from negative pi over 2 to pi over 2. Where does that occur? That occurs right at 0 radians. Again, always have that unit circle kind of in the back of your mind here. Okay? So since we're looking at a unit circle, we're essentially looking at ordered pairs. Okay? So in our case, 1, 0, and keeping in mind that an ordered pair is being based off of the angle measurement. So it's the cosine of the angle and the sine of the angle. Our angle just has to be in between negative pi over 2 and pi over 2. And so 1, 0 falls right into that. So you'll notice that, yeah, I could have put a negative 1 here, but that would put me over on this side. It's outside of my interval here. So my interval is either 90 degrees, or so to speak, to the positive direction, or 90 degrees to the negative. If I'm over here, I'm past that. So it eliminates using a negative 1. Now, let's look at some more. Let's look at a couple of others. Now, obviously, there's going to be more complex type of situations you run across. And so we have to take a look at how those will work. Again, getting it back to that sine and cosine. All right, so let's say we change it up. And let's say I'm going to use the other notation here. So I'm going to use inverse tangent. In this case, though, of the following. Negative radical 3. Now, again, the goal is always to figure out what radian angle we're talking about. So we're going to set that equal to theta. Again, our goal is to figure out the angle and now convert it. All right, so I'm going to convert. And I'm going to say the tangent of my angle that's in question needs to be equal to negative radical 3 over the interval that's restricted. Negative pi over 2 to pi over 2, non-inclusive. Now, just like we saw with sine and cosine, what the interval is doing is limiting you to 2 different quadrants. Okay, again, using the unit circle as kind of our picture to work with, we're limited to negative pi over 2 up to pi over 2. Quadrants 4, quadrants 1, knowing a negative angle or a positive angle. Looking at the value of tangent here, that the tangent of that angle in question is negative, narrows us down to the single quadrant we must be in. Okay, so again, what's going to help here is to have a little mental picture of it. Okay, so where is tangent going to be negative? It has to be in quadrant 4. So it's telling me, because the tangent is a negative value, my angle will be a negative angle. Okay, and again, now I'm going to make a concentration here of somewhere in quadrant 4. Now, think of an ordered pair here for a moment. This helps you with signs, positives and negatives here. Cosine of an angle, sine of an angle. What do we know about ordered pairs in quadrant 4? The cosine value is positive. The sine value is negative. Now, again, we don't have those tangent values actually calculated. So we're going to transition to sine and cosine. All right? So the sine of the angle divided by the cosine of the angle is equal to negative radical 3. Now, because the sine value here is the negative, I'm going to leave that negative with the radical 3, and then I'm going to list it over 1. Now, I already know people are looking at this going, oh, wait a second, Mr. Varst, those are not showing up on the unit circle. Well, not quite yet. Look at your unit circle a little more closely. And you can look anywhere on the unit circle that is not on an axis. Okay? So disregard these 4 positions and look at all of the cosine values and sine values as you go around the unit circle. Look at all of the denominators. What number are they? Every single denominator, no matter what position you're in, they're all 2's, aren't they? It's either a radical 3 over 2, a radical 2 over 2, or a 1/2. positives or negatives. So what is this really telling us then? These two numbers that we see at this point are numerators, which means if those are numerators, we could essentially say they have the same denominator because they reduced. So we could make the argument here and say in these situations, my sine value radical, negative radical 3, the cosine value of a 1, make those numerators over the common denominator of 2. Negative radical 3 over 2 and 1/2. Now when you match up the sine of the angle and the cosine of the angle, you're essentially identifying the numerator is the sine value on the unit circle. The denominator is the cosine value on the unit circle. I just have to name the angle in the correct direction. Now, because we are going negative radical 3 over 2 and positive 1/2, it looks like we're kind of dealing with this position about right here, where we have 1/2 negative radical 3 over 2. That would be what angle? Now, if you said 5 pi over 3, what would be the problem? It's outside the interval. So keep in mind that you're rotating negative when it comes to tangent. So it would be not a 5 pi over 3, but a negative pi over 3. Okay, so be very, very careful. It's very easy to just write 5 pi over 3 because that's the known unit circle value. I have to keep in mind my rotation here. My rotation is this direction. Okay, I'm going in the negative direction for the angle, so be very careful about that. So literally, everybody, you're doing the same basic thing. You're just converting then from tangent to sine over cosine so you can identify those values on the unit circle. Now, if we take that further, let's take a look at the cotangent graph. You're essentially going to build it the same way. Okay, so I'm going to go a little bit quicker here on this idea of cotangent. Okay, so let's say we take another function. Let's say we just call it g of t. Okay, and we're going to look at it as the cotangent of t. All right, now I'm going to build it the same way. Now, you're probably going to notice, if you've got in mind already what cotangent is looking like, is that if I start looking at the positions of cotangent graphs, we're going to make essentially the same type of reduction in the domain. All right, so I'm drawing this pretty quick here. But you would recognize from previous learning here that with a cotangent graph, you have vertical asymptotes at 0, at pi, and at 2 pi. And then also if I went in the negative direction, I would have one at negative pi. Okay, so these are known values, okay, are known situations here. But our cotangent graph ran from 0 to pi in this direction. So it was like a tangent graph shifted upside down, but in a little bit different location. And again, that repeated itself because of the periodicity of that function. But again, we're just drawing different ones, and we can see already this isn't going to be one-to-one. So if I don't limit my domain, cotangent of a graph or cotangent of a function cannot have an inverse. So what do you think we'll limit it to here? That involves the 0. Notice it kind of matches up with what? keep the 0. Normally we want to follow a positive direction. So I'm going to keep the 0, get rid of everything to the left. And I think I can get rid of everything from pi. So our restricted domain here to get a one-to-one function will be restricted when we restrict to what? Again, non-inclusive endpoints, but 0 to pi. So we're going to allow inverse cotangent to exist anytime we allow tangent or restrict cotangent, restrict cotangent to an interval from 0 to pi. Okay? So when the cotangent of the angle is restricted to t being within 0 to pi, the inverse cotangent of the angle will exist. Okay, so very similar to what we saw with sine and cosine. Tangent now, the cotangent the same way. We're just limiting the interval that we're going to allow tangent or cotangent to exist. Cotangent from 0 to pi, non-inclusive again because of the vertical asymptotes. So now we're just doing the same thing. Let's look at a couple of examples. Now, keep in mind that as we do more examples involving cotangent, some of the processes that you're going to use to figure out the unit circle values also apply to tangent. Okay? So don't just limit yourself and say this is only going to happen with cotangent. We're going to see the same kinds of manipulations occur with tangent. Case in point, let's say we start with another evaluation. And let's say we have the arc cotangent, so arc cotangent of radical 3 over 3. All right. Pause it for a moment and go ahead and make the transition here. Keep in mind the interval you must be restricted to. Go. All right. So again, anytime we're finding inverses, our goal is always to find the angle. Okay? So we're always looking for an angle when we're dealing with inverses. Okay? Just like sine, just like cosine, just like tangent, let's convert it to something we're more familiar with. In this case, the cotangent of the angle I'm looking for is equal to radical 3 over 3 on the interval from 0 to pi. So hopefully you got that part down. Now, what quadrants is 0 to pi? Now again, keep in mind it's non-inclusive, but if you're limited to 0 to pi, you're looking essentially through quadrant 1 and quadrant 2. So again, the interval limits us to 2 quadrants. The value, okay, the radical 3 over 3, determines the individual quadrant. It's positive. Now, cotangent can only be positive when sine and cosine are both positive or sine and cosine are both negative. Well, that kind of takes out quadrant 3 because we never use quadrant 3 for inverses. It puts us in quadrant 1. So we know that somewhere in here, our angle that we're looking at has to fall within quadrant 1. Okay, so again, the interval narrows you down to 2 quadrants. Positive or negative on the actual values I'm given determine the individual quadrant. So it narrows you down all the way. So we're looking at a quadrant 1. Now, just like we did with tangent, let's convert the cotangent. Okay? So cotangent could be written as what? Cosine over sine. All right. Now, the nice thing here is I've already got a fraction. Oh, but wait a second. Yeah, the upper number seems to be okay because I recognize there's radical 3's on the unit circle. But can a 3 ever exist on the unit circle in terms of a sine or cosine value? Maximum that a sine or cosine value can take on is 1 or negative 1. Those are the maximums, highest value, maximum, lowest value. Okay? Or maybe better stated, a maximum and a minimum. Okay? So my sine values and cosine values have to run between negative 1 or positive 1. So I can't say the sine of the angle is 3. That is invalid. What's going on here? How am I going to figure this one out? So this is another interesting situation here. That 3 is the problem. Now, you've had many situations when you've dealt with radicals, but the radical is in the denominator. And you could never leave your answer with that radical in the denominator. So what did you do? You rationalized. As a case in point, like if I had, let's say, 3 over radical 7, you could not leave an answer as 3 over radical 7, so you rationalized it by multiplying by radical 7 over radical 7. So we'd have a denominator that is legal to use. That's essentially what this form is already. It's a rationalized form of our value. So what we need to do is one of those rare occasions that you practiced once in a while where you actually need to rationalize the numerator. Watch what happens here. If I rationalize my numerator, look at what occurs. Radical 3 times radical 3 is 3. The denominator is 3 radical 3. You can now perform a reduction of 3's. And notice that now we're looking at 1 over radical 3. Cosine of the angle, sine of the angle. That's the difference here, is that you will have times where you'll have to rationalize the numerator. Now, I know I'm running out of room as I get over here, so I'm going to remove this little piece here so I can keep this visual for you. But now let's keep going. Think of those denominators that exist for all fractions, sine and cosine, not on the axes. They're all 2's. So I can look at my numerator as being 1 over 2. I can look at my denominator as radical 3 over 2. And now, make the connection. Now we can see that our cosine value is 1/2, a known unit circle value. The sine value is radical 3 over 2, the corresponding unit circle value. Where is sine radical 3 over 2 and cosine 1/2? Straight identification. Positive angle in this case. Cosine is 1/2, sine is radical 3 over 2. That's going to happen at pi over 3. So these are doable, everybody. It's just a matter of how are you going to handle certain situations. This is one of them where I've got to deal with the fact I actually have to rationalize a numerator. Last example. Now you'll notice we're running into situations here. You're hitting almost every possible situation you can with a unit circle value with tangent and cotangent. Okay? We've seen it where we've seen a 1 over a radical. Okay? That's here, after a rationalizing. We've seen it with a radical over a 1. We've seen it when it's been equal to 0. Well, what if we had this one? Final problem. Inverse cotangent of, let's say, -1. Pause the video. See if you can take yourself all the way through this problem and see if you come out correct. Go. All right, here we are. Final problem of the day. Again, the goal with any inverse is to figure out an angle. Convert, keeping in mind the restricted interval. So we're looking for the cotangent of an angle equal to -1 on the restricted interval of -π/2 to π/2. At this point, we hopefully have switched it to cosine over sine. Okay, so the cosine of the angle over the sine of the angle must be equal to -1. And again, I'm going to list that over 1. So again, keep in mind where things are at here. -π/2 to π/2 is actually not the correct interval, is it? That's my mistake. See, I'm human just like all of you. I got to go from where? 0 to pi. Okay, got to make sure I'm in the right quadrants. I'm human. One more hair lost. Don't worry, there's still more to go. Now, if I convert to cosine over sine, keep that negative in the numerator, this is going to tell us that I'm looking at a cosine value that's negative, a sine value that's positive. I'm in quadrant 2. Okay? So I know that my angle has to be somewhere in quadrant 2 on the unit circle. So if I go and look, -1 over 1, well, that doesn't happen. We do get 1s and we get negatives, but they're not in the same positions. Now we have to keep in mind this -1 is a reduced value. So what we need to recognize with both tangent and cotangent is that if I get a -1, what that's telling me is that sine of theta has to equal cosine of theta to get a 1. So I need to visually know, when are my sine values and my cosine values the same numbers, but their location determines the positive and negative. Okay, so again, location meaning unit circle. Well, if I come all the way over here, I notice that I'm going to have a cosine value of radical 2 over 2 that's negative, a positive radical 2 over 2 for the sine, positive. But look at the sine value and the cosine value. Don't worry about the negative here. Just think about the numbers. They have to match in order to reduce to a 1 or a -1. So we need to recognize that if it's a -1 or a +1, my sine and cosine values carry the same numbers. Just one's positive or one's negative, depending on the quadrant. So we would have negative radical 2 over 2 over a positive radical 2 over 2. And now I can identify the cosine value, negative radical 2 over 2, the sine value, positive radical 2 over 2. We're looking at this angle right here. What angle is that? In radians. We should hopefully come up with an angle of 3 pi over 4. Now, keep in mind, just like you saw in some sine problems and some cosine problems, is that if you start getting real life applications, a lot of times you might be in a degree measure, okay? So be careful of that. Be watchful of what it's saying within your application problems. If they're giving you things in degrees, you can be in degrees. If they're giving you information in radians, stay in radians. Okay? So don't lose that thought. But literally, everyone, you should be seeing the same kinds of transitions with tangent and cotangent as you did with sine and cosine. But always, always, always make sure you list that restricted interval when you convert to what's more familiar to you. Most common mistake, people think they don't need this and then they write down a wrong angle. So be very careful there. All right, you're on your way. Good luck. Take care, everybody. We'll see you in the next one. Bye-bye.